Okay. Next up, we have a conversation on technology use in the energy industry with Kyle Summerfield, who is the program manager, and James Amato, who is an associate research professional and division manager, both of whom are employed at the 3D Visualization Center inside the School of Energy Resources. Their services have really expanded over the past few years, and we're super excited for you to hear about their latest technology and their most recent field adventures.
All right, thanks, Austin. Everybody can hear me okay? Yep, I can hear myself okay. So yeah, I'm Kyle Summerfield, and I'm here with James Amato. We're going to cover a few different topics today. So this is an overview of the topics that we will cover. So we're going to talk about our transition to a service center. We're going to talk about hyperspectral imaging in particular, and that device is over on the table over there. We'll be kind of hanging out throughout the day if you have questions about that after the presentation. James will be covering the hyperspectral topic. I'll be covering photogrammetry and Gaussian splatting after that. If you don't know what those words mean, calm down. It'll be okay. We'll get there. We will try to maintain a healthy and platonic distance while sharing the mic, but we'll be kind of passing it back and forth as we progress here. So if we can move to the next slide there. This slide covers the topics or the services that we'll be providing as a service center to UW. I'll talk briefly about software development, 3D modeling, environment capture, and consulting, and then James will cover the other sections. So we build software for all kinds of different platforms. While we are originally kind of primarily known for immersive technologies like what was the Cave at the Viz Center, if you've been there before, virtual reality and augmented reality displays, we also develop for desktop, mobile, web platforms and stuff. You'll see one of those tools later in the talk today. 3D modeling, we do bespoke, hand-modeled objects as needed for like mine safety training applications and other industry training applications. We also do 3D capture of environments and objects, materials, and yeah, you'll see some examples of those as well. And then we are also available for consulting or training for GIS, UAS, and remote sensing applications. I'll pass over to James to take the other topics here, and you'll hear from me later.
Hello, everybody. So, yes, my name is James Amato. I oversee the GIS and remote sensing capabilities at the School of Energy Resources. So in addition to the other capabilities that are being offered through the newly established Service Center, we also offer GIS and remote sensing capabilities. GIS, Geographic Information Science, right? This is the science of where. It's a mapping technology. It's a way that you can build models of the topography of the land, right? On the surface, additionally in the subsurface. So we have expert GIS technicians and analysts. We build a variety of geotechnical databases and offer a variety of other GIS analyst and cartographic services. Shortly after now, I'll also be talking about a new program that we recently stood up, our remote sensing division. We do a variety of different types of imaging, from putting cameras on drones, putting cameras on tripods, and also bringing these cameras into our laboratory to do lab-based measurements. We do photogrammetry services, we do hyperspectral services, and we'll soon be doing LiDAR services as well. So again, we recently stood up the Service Center. What does that mean? We are now an official UW Service Center. Well, that means that we provide these services not only to researchers across the campus, but we also offer these services to other academic institutions as well as to private industry. So the Service Center makes these services broadly accessible. We can streamline billing on government-sponsored grants, provide a consistent cost recovery model, and help sustain planned equipment investments. So basically, in order to become an official service center at the university, we need to have very transparent rate structures. These are public rate structures. We can't compete with industry, right? We need to be equal with industry. So we do offer multiple different rates. There's an internal rate for the University of Wyoming researchers. There is an academic rate for outside academic institutions, and then there's an external rate for private industry and other non-academic organizations. Some of the challenges that we faced standing up this service center is that some of the technologies that I'm about to introduce Only a very small handful of people in the United States are doing these things right here. So our drone-based hyperspectral imaging program is very unique. We are very excited to bring this capability to the University of Wyoming and offer this service across the Rocky Mountain region. So I want to talk about hyperspectral, and I'll kind of give a little bit of a layman's term of what exactly it is. But our mission is to advance the use of hyperspectral imaging by educating the next generation of practitioners, developing proof of concept solutions for academic, state, and industry partners, and providing expert consulting and operational services. So what is hyperspectral imaging? It's a technology that was developed by NASA in the 1980s. It's a technology that acquires and analyzes reflected light in different regions of the electromagnetic spectrum. Utilizing hundreds of continuous bands, hyperspectral imaging provides a wealth of spectral data compared to the tens of discrete bands often used in multispectral imaging. It is because of this refined spectral resolution that this technology can be used to provide direct identification and analysis of surface materials. Many subtle objects and material substances can be uncovered and extracted for detection, discrimination, classification, and quantification. It is a non-destructive technique. So, in simplest terms, I like to compare these different types of imaging, RGB imaging, multispectral imaging, and hyperspectral imaging, to boxes of crayons. So when I was young, growing up, I would go out to a Denny's or a Perkins and sat at the table, and the waitress would have came over and thrown a 3-pack of crayons on the table for me to sit there and color, right? And that's kind of what RGB imaging is. You have 3 crayons, you have 3 bands. Those bands are red, blue, and green. This is what we see with our eyes. This is visual light. We can blend those 3 colors together, and this is what we see. So this is the type of imaging that's on our cameras and on our smartphones. It's great. It allows us to take pictures and see the world, right? But we're also looking into just a very small gap of the entire electromagnetic spectrum. And if we can see into other parts outside of visual light, that gives us opportunities to do lots of different type of analysis. So multispectral imaging is kind of like that 10-pack of crayons that most of us had growing up. You've got 10 very distinct colors, you can see the visual light, but you've also got 7 different crayons that can look into very, very discrete regions along that electromagnetic spectrum. And hyperspectral imaging is like that 150-pack of crayons that I didn't get that growing up, it was way too expensive, but maybe some of you had that. But that's what hyperspectral imaging is, right? You have all these crayons, you have all these different tones and shades, right? You can really, really color a pretty picture. And all those crayons represent all these different bands, all these little different windows that we can look across the electromagnetic spectrum, and we can conduct these really neat analyses that I'm about to show you. So what is hyperspectral imaging used for? Well, at the School of Energy Resources, we use it for mineral, lithological, and alteration mapping. You'll see shortly that we can scan the Earth and we can create these beautiful mineral maps of the surface. We can use it for ore waste discrimination, feedstock prioritization. In the realm of environmental monitoring, it can be used to track vegetation condition, land soil change, water quality indicators, and even now gas detection monitoring for emissions. In the world of agriculture and forestry, you can use it for crop health and stress monitoring, early disease detection, moisture nutrient pattern mapping, and species invasive vegetation identification. Hyperspectral imaging is the technology that sorts your plastics at the recycling center, right? It can be used to identify different plastics, paper, glass, textiles, and common contaminants to improve automated sorting accuracy. In the food industry, it's used to detect contamination of foreign material, assess ripeness, freshness, classify quality, and identify bruising defects. In the pharmaceutical industry, that's very popular right now with lots of pills coming in overseas, it can be used to verify ingredients, detect contamination, check blend uniformity. And in the world of cultural heritage and archaeology, it's a non-destructive analysis for paintings and artifacts. So at the School of Energy Resources, we've stood up this hyperspectral remote sensing program primarily for mineral exploration. There's a big push right now in the state to find those critical minerals and rare earth elements. And this is a new quantitative technology that is going to help us in the field of exploration. So certain minerals are diagnostic of certain wavelength regions. So you need the right camera with the right sensors to see the minerals that you're looking for. And when we do spectroscopy in the infrared range of the electromagnetic spectrum, we usually like to divide that up into 4 different bins. There's the visual near infrared, the shortwave infrared, the midwave infrared, and the longwave infrared. Looking at this image, you can see certain minerals in certain groups, right? So our camera that is on display over there, we have 2 sensors on that camera that can look into the visual near infrared along with the shortwave infrared. So with that visual near infrared, we can find things like oxides or rare earth elements. And in that shortwave infrared, we can look at things like carbonates and sulfates and varieties in clay mineralogies. We can't see all minerals. Some minerals are more spectrally active than others, but we can also see other minerals that might suggest that there might be an ore deposit in the subsurface, so to speak. So I won't get into this too much, but this is basically how it works. The squiggly lines you see on the screen are referred to as spectra. And in those spectra, you see dips. Those dips are referred to as absorption bands. And that's where a material soaks up and absorbs all the light. And the geometry and shape of those absorption bands are diagnostic to different surface materials. So every mineral has a spectral thumbprint. Every type of plastic has a different spectral thumbprint. This is where we can use it in the pharmaceutical industry, right? Ingredients have different spectral thumbprints. And that's how this basically works, is we basically are scanning the earth and looking for these different spectral signatures. So again, there's not a lot of people doing this right now. So hyperspectral imaging has been around since the 1980s. Again, it's a technology that NASA developed. These cameras are mounted on satellites. These are satellites that are orbiting different planets in our solar system, right? This is a tool that we use to figure out the composition of different atmospheres in planet surfaces. And it's only recently that these technology between drones and cameras have gotten to the point where we can mount them on drones. So satellite remote sensing is great. You can cover vast areas, but it's very coarse imagery. In the world of remote sensing, we're always talking about pixels. And those pixels are what we look at to do our analysis. And with satellite technology, those are really, really big pixels. They're like 30 meters by 30 meters. So they're great if you're covering a vast area. But if you're looking at maybe a smaller application or looking across a mine, right, that can introduce a lot of false positives. So through time, these cameras have then been mounted on airplanes. Those pixel sizes have gotten smaller and smaller and smaller. And now it's with this technology that instead of being 30 meters by 30 meters, we're now creating pixels that are 6 to 7 centimeters, right? So we can really do characterization at an outcrop scale. But the slide is basically showing the 3 different aspects of doing or using this type of technology. The first step is doing data capture, right? And there's a lot of hoops we have to jump through. We're all FAA licensed pilots with the Federal Aviation Administration. We have to follow all their rules and regulations. The University of Wyoming has a UAS drone committee as well. So everything that we do has to be submitted through the university to make sure that we're in line with university policy. But there's a lot that goes into the flight planning. Depending upon what we're monitoring, we could be looking at bare rock, we could be looking at vegetation. There's all different parameters that we need to set the drone, how high we're gonna fly, how slow we're gonna fly, and so on. But after we do that, we're left with what we call raw radiance data. And when you put a camera on a drone, and that drone is flying in all different angles, up and down, and being blown in the wind, there's all different types of corrections that we need to do to it to get it into a usable state for analysis. And so we have to then apply a variety of different radiometric, geometric, and atmospheric corrections. There's aerosols in the sky, depending upon the sun angle. This is a technology that uses natural sunlight outside, right? So we don't want to capture on cloudy days. And ultimately, when we're all done, we have a reflectance cube. And we call it a cube because every pixel has an X and Y coordinate, right? But there's also a Z coordinate. And so we talked about hundreds and hundreds of bands, and this camera has 500 bands. So you can kind of think of it as every pixel you can look at 500 different ways across that electromagnetic spectrum and find those little detailed signatures to tell you what that substance is. Once we have a usable hyperspectral data set, there's all different types of spectral algorithms that we can use. Large entities like the US Geological Survey, the Jet Propulsion Laboratory, a lot of these different large entities, NASA, have developed all these different spectral algorithms, and they've also developed spectral libraries. The USGS spectral library is probably one of the most well-known, but this entity has gone through and scanned thousands and thousands and thousands of different materials and have captured those spectral thumbprints, and they're all sitting in a library. So they've scanned thousands of minerals, they've scanned plastics and building materials and everything like that. So they build these libraries with these spectral thumbprints. We can take our raw data sets, run them through these spectral algorithms, they look at that library, and then we start creating matches and creating mineral maps. So this is an output. Some of you might be familiar with, there's an old pit in Sabile Canyon near Johnson Reservoir on your way to Wheatland. And so we used this site last year as kind of a testing facility. And so we went out there and scanned, and initially it's a non-operational magnetite ilmenite pit, but we did a scan. And so because we have two sensors, we have that veneer sensor and SWIR sensor, we have two different maps for every capture that we do. But you're looking at basically a mineral map, the image on the right. It's showing a distribution of hematite and goethite in the visual near infrared range. Now, this camera is a very versatile camera, right? We can mount it onto an aircraft, we can mount it onto a drone, we can put it on a tripod, and you know, the summer seasons are very short here in Wyoming. So we like to take our camera and bring it indoors during the winter months, and then we can start scanning drill core and hand samples, right? This is a technology that can't penetrate vegetation and it can't penetrate the surface. But being able to scan drill core that comes out of the ground, we can get surface analysis as well as subsurface analysis. So cutting edge technology, but every technology has its limitations. One, this is a very complicated technology, right? Hyperspectral imaging has been around, but now that these cameras are putting on drones, there's not a lot of standardized workflows. This is all being put together as we speak. Again, we're one of the only few entities in the United States that are actually doing this type of imaging right now. It's also very expensive. It's gotten cheaper and cheaper, but you know, cameras can run hundreds of thousands of dollars, drones can cost hundreds of thousands of dollars. It's a lot for a mining company that is interested in this technology, and that's kind of where the Spiz Center has come into place, right? We've gotten tons of interest from mining companies that are interested in standing up their own programs, but before they invest $500,000 into it, they want to make sure that this technology works, right? And that's what we're here to do, is to help build these proof of concepts and show that this technology is successful and to assist them standing up their own programs or acting as a service provider. So this sensor is what we call a passive sensor. You have active sensors and passive sensors. An active sensor is maybe like a LiDAR scanner that spits out a little laser beam, and that laser beam bounces off the earth and comes back and is measured in the sensor. A passive sensor doesn't emit any energy. It only analyzes, acquires reflected energy. So it's using sun as its source. So we have to go capture on those big blue sunny Wyoming days, and luckily the sun shines in the state quite a bit, right, compared to other places in the Midwest. But yeah, if you capture on a cloudy day, you're degrading the signal, and it will create issues later on when you're trying to do your supervised classification. It's sensitive to air quality. We went out in the field, we got out there at sunrise last summer, and the sky was just orange, right? Utah was on fire, and all that wildfire smoke blew up into Wyoming, and it created really hazy skies. Again, it's not really worth capturing because you're going to get really a low signal. It's also very computational demanding in extremely large data volumes. When we do a capture, that capture could be tens of hundreds of gigabytes. And then we have to clean that data up and process it, which turns into more tens of hundreds of gigabytes. So we also have issues storing it, right? We can't just throw it on the cloud because we need to run this through different algorithms and do analysis on it. And so everything needs to be local. And then lastly, limited penetration depth, right? This can't see through vegetation. This is just not, it's not going into the earth, right? You're just getting what's on the surface. So Wyoming, we don't have much vegetation here. We have lots of bare rock. So this is a great state to do this type of imaging, right? If we were back in Wisconsin where there's just vegetation, if you're doing vegetation analysis, that's great. If you're looking for the actual soil or the minerals and the rocks, it's a different ballgame. All right, so over there is our current drone. This is a drone by a US manufacturer, Harris Aerial out of Florida. These are American-made drones. These are NDAA compliant drones. NDAA stands for the National Defense Authorization Act. You might have heard there's a big push to not use Chinese drones anymore or drones from our foreign adversaries. So these are drones that have been approved and signed off by the federal government that we can use on federal contracts. It's a great drone. It's an octocopter, which means it's got 8 propellers. And the idea with it is redundancy. The payload is very expensive, hundreds of thousands of dollars. You know, if we have an issue in the sky, if 2 motors fail, we can still land that drone very safely and not crash it. In the world of flying drones, there's a threshold at 55 pounds. If your drone takeoff is under 55 pounds, it's very easy to fly drones in the United States. As soon as you go over that 55-pound threshold, there's a lot more red tape and a lot more hoops you have to jump through with the Federal Aviation Administration. And so we are maxed out on that drone. We got to about 54 pounds, and we have some limitations, right? Flying drones in Wyoming is a little bit tricky. We're at high elevations. The air is thinner here, right? That means the drone has to work harder. It means it drains the battery quicker. That drone, maybe at sea level, could stay in the sky for 30 minutes. But if you bring it up to 7,000 feet, that drone now might be able to stay in the sky for 10 minutes. It's also extremely windy here in Wyoming, which means the drone has to work harder. It drains the battery quicker. So the drone on the screen is a drone that we are in the middle of procuring right now. And this is a significantly larger drone. That's got about a wingspan of 6 feet, and this has about a wingspan of 10 feet. That drone can carry about 16 pounds. This drone can carry about 88 pounds, so like a small child. So this drone will help us be way more field efficient, right? We can put a gimbal on this and stabilize our camera. We can fly for longer periods in the sky. We don't have to be so concerned with windy conditions. The spectrometer, the camera, we call it a hyperspectral imaging spectrometer. This is a state-of-art spectrometer. It's by a company called HiSpecs. HiSpecs is a global leader in hyperspectral imaging based out of Norway. This camera, again, is very unique. We have 2 sensors on it. We have a visual near-infrared sensor. We have a shortwave infrared sensor. We also have a LiDAR puck on it. So every pixel that we're looking at is co-aligned and co-registered so that we're capturing the exact same pixel in each of the sensors. And again, it's a very versatile camera. We can put it on an airplane. We can put it on a drone. When you're flying over open pit mines, there's a lot of vertical walls. There's a lot of vertical exposures. And it's very difficult to capture those faces from the air. So we can take this camera and we can put it on a tripod, and then we can scan those high walls in mines, right? And this helps mining companies figure out which direction that they want to continue digging into the wall. And again, lastly, we can bring it into our lab. We've just built a state-of-the-art darkroom. When you bring it indoors and you don't have natural sunlight, you want to have very controlled illumination. So we just built a darkroom in the Energy Innovation Center that will house this piece of instrument. So in the off-season, we can scan tons of drill core and hand samples. One other important piece of equipment or instrumentation in this program is called a field spectrometer. This is a little backpack unit that we walk around in the field with. This field spectrometer, it doesn't image, it doesn't paint a picture, so to speak, like that camera does. But what it does is we can point it at a material and zap it, and it shows us that spectral thumbprint. And this is important for ground truthing. Traditionally used with satellite technologies, you wanted to make sure what the satellite was seeing. If the satellite sees gold, we want to make sure that the image spectrometer or the field spec on the ground also sees gold, right? So it's a way to do ground truthing and furthermore with calibration. We can also bring this into our library or our darkroom and create our own spectral libraries. There's a big push for uranium right now. So the USGS Spectral Library, when they developed it 20 years ago, I think there were concerns about putting all these different uranium waste thumbprints up for public use, right? Concerns of foreign adversaries looking at that. So we're working on a mine waste project right now with uranium, and we're developing our own spectral libraries. We're grabbing hand samples, crushing them up, bringing them into our darkroom, zapping them, and getting those spectral thumbprints so that when we fly over, we know exactly what we're looking at. It's also not a bad idea to validate things even more. We'll grab hand samples and we'll make sure that, okay, the drone sees gold, okay, the field spec sees gold, and let's throw a sample in the lab and do some quantitative XRD analysis and make sure everything lines up, right? So it's all different forms of validation to make sure our drone is seeing what we think it's seeing. And I will now turn this over to Kyle Somerville to talk about Gaussian splatting and photogrammetry.
Okay, I'm back, and for that I apologize. While I'm apologizing, I forgot to go to this slide when James advanced it. This were those squiggly lines that he was talking about with those absorption bands. So mea culpa there, and I submit to the students an example of integrity. Okay, so I'm going to talk about structure from motion, and that's going to take two forms. One's photogrammetry, and one is Gaussian splatting. Before I get too far into this, I'd like to see a show of hands, if possible. When I say photogrammetry, who has something with that term? Anybody? Okay, couple. Okay. If I say point cloud, does that mean anything to anybody? A few more. Okay, great. Okay, structure from motion. What we're doing in this case is getting 3D output from a series of 2D images. So we can use any standard camera. This can be drone mounted, it could be hand mounted, it could be your smartphone. And we're taking a series of photos of an object from different angles. If we have enough angle coverage, we can then derive the 3D shape of that object or environment. So you can see in this example, each of those little prisms is a frustum of a camera that's a different position. And then the series of dots that you're seeing in that image that's a sparse point cloud. So those are called tie points. We're looking for common occurrences of a given feature across multiple photographs. Then it's kind of a simple algorithmic approach to back engineer where those photographs were taken from and then create the 3D model after that. So this gets used in a bunch of different places. It's not just photogrammetry. We use it for SLAM tracking, so simultaneous location and mapping. So robots that have a camera mounted, they're using that to keep track of their environment and not run into things. VR headsets are using the same basic process to keep track of where you are in a space, or augmented reality displays. We can also use this for plane detection, so if we need to understand something about the environment, like the IKEA app, right? When you download that thing and you want to see if that couch is going to fit in your living room, it's doing basic plane detection to see where to place that couch against your wall or on the floor. We can also use photogrammetry or structure from motion approaches to retexture things. So sometimes I'll get like a 3D model that's been captured from some other process, like a structured light scan or something, and the model's great, but the texture is garbage. So I can then take that same model, do a photogrammetry pass, use their really high fidelity geometry and retexture it. So apply colors from the photogrammetry set. Okay, we're gonna compare photogrammetry to Gaussian splatting. I realize I haven't told you what Gaussian splatting is yet. This is suspense and foreshadowing. It'll be exciting later. But the photogrammetry thing is a triangulated mesh. So this is what you're used to seeing in a rendered computed environment. So it's a series of points, lines, and triangles, and those can be lit in all the traditional ways. So if you have it in a real-time rendering environment and you have a digital light and you move that light around, it will shadow and relight correctly in sync with the rest of the environment. I will show you some examples of that. Photogrammetry is relatively easy to edit and retopologize, so you can reduce the triangular complexity of a given mesh. There's a lot of workflows that are established to do this. This is much more difficult to do with a point cloud or photogrammetry without losing like surface fidelity. And this is actually changing, but Geolocation is supported in most GIS environments. So a photogrammetry model that you capture of like a pit or a structure or a site that you might want to do reclamation on later, those are all supported in like ArcGIS environments. Gaussian splatting is happening there too. There are weaknesses to a photogrammetric approach. So it's bad at capturing very thin objects, dark, reflective, and it requires really thorough coverage of an environment or an object. It also does a terrible job of getting the surrounding context. So if you need to understand the whole landscape around a thing that you're capturing, photogrammetry, probably not your approach of choice. Gaussian splatting would be that approach. So point clouds are basically X, Y, Z positions and RGB color values. So I'm capturing a bunch of different points from an environment or about an object, and I'm saying it is here in X, Y, and Z space, and it has the following RGB values. Gaussian splattings are fancy point clouds. There are more floats, so each point has additional data associated with it. That data is as follows. It's called Gaussian splatting because there's a Gaussian blur that has been spread, distorted across usually a quad. I won't get too into that, but you can see an image of that on the bottom here. So that looks like a bunch of garbled nothing. I'll show you what the inside of that looks like in a minute. But each of those points is a Gaussian blur that has been distorted through a machine learning algorithm to best approximate how that thing will look from any given perspective. This will make sense. There are additional floats that will tell you what colors those points should be from different points of view. So this is how we get correct reflection, refraction behaviors from materials without doing any of the complicated ray tracing math that modern GPUs can do. So when I look at an object from the top and it has some color property that is only visible from that area, a Gaussian splat will give you that information visually, whereas a triangulated mesh cannot do that. So there is free reflection and refraction. It handles thin, dark, transparent, and reflective objects much better than photogrammetry does. It has significantly lower geometric complexity. There's an asterisk, I'll elaborate. And it does capture the surrounding context. Currently, it is, even though the geometry is much more efficient, it's harder to render. The reason for that is that modern GPUs are not well optimized to do lots of transparency. I'll show you before I talk more about that. Okay, comparing output. So the mesh on the left and the splat on the right are from the same input data set. You can see the photogrammetry model has about 30 million triangles and about 14 million verts. The splat model on the right has 2.5 million triangles and 7 million verts. So from a geometric perspective, so from a data size perspective, this is a much smaller object to pass around like a network or a flash drive or whatever. You can also see, maybe not from that far away, but all of those posts are well captured in the splat and not the mesh. I think I have yeah, perfect. So on this slide, you'll see the wrought iron fence that surrounds that building is basically lost. It's just a bunch of garbled geometric mess. It is retained in the splat model. But the trade-off is the splat model is a little blurrier. It's not as sharp and refined. So if that's important, a photogrammetric mesh may still be useful. This is a video. I said that you could relight photogrammetric models, and that is true, but you're also capturing all of that shadow data in the color values when you're capturing a model. So you can see this model that we captured is lit. There was the sun, and it was casting shadows. And so that's captured in the texture. I think if I do this, oh yeah, we're not synchronized. If you advance the slide, it should play the video. Okay. Okay, so I'm moving around that model just to prove that it's really 3D. Now I'm grabbing that light source and moving that around. You can see that it is relighting, but we still have that shadow data baked in there. So there are a series of processes you can do called delighting that can correct for that. This is a model that has been delit, so it does not have shadows built into the texture, so you can see that it is fully correct as I move the light around. Okay, this next part is going to be a fun experimental hybrid presentation thing. So Jerry, if you can pull up the splat viewer. Okay, cool. So this is our online splat viewer. So this is hosted on a web browser. This could run on your phone. It's very well optimized. If you step outside of this building, you will see this object. So if you can kind of orbit around it, you can see, like, if I were to make this out of triangles, I would have to devote so much to that vegetation and so much to each of those brick surfaces, right? But in the Gaussian splat model, I can render this really efficiently on really modest hardware. Could you load the coal brick house model? It's in that drop down. This is the model we were looking at earlier, and you can see that the wrought iron fences are retained. If you look at those windows, if you zoom in a bit, Jerry, you can see as he moves around that they appear to reflect and refract light correctly, even though there's no geometry to do that. If you're interested in how that works, I gave a talk about it. If you search my name on YouTube in Gaussian splatting, you will see that talk. Please watch it so that my view count surpasses James's view count on that same forum. Okay, and let's pull up the road cut. So I said that Gaussian splatting does a good job of capturing the environmental context, and this is an example of that. Yeah, if you can just move around a little bit. You can see this is a much larger environment. This is a road cut up by Moab. And here you can kind of see the trick that's happening here, right? So the splats are being skewed and distorted and recolored depending on how you're looking at them. So why would we use this in the context of land management? Well, what if you did need to do reclamation? You needed a really compelling before and after. Your before, you could go take a bunch of orthographic photos. You could use a DEM, but you're not going to capture undercuts. You're not going to capture like complex superficial features. This would allow you to have that sort of ground truth. This is what it was like before, and this is what we need to get back to. And you could show that to a client, right? Okay. So that is everything we have for the talk right now. Should be plenty of time for questions and a fun final slide. There you go. Okay, yeah, that's us for today. We are available for questions if there are any.
And we'll also be here all day, so feel free to come over, pick our heads, possible projects. We love collaborating with students in industry, so if you have ideas, please reach out.
Thank you very much. For the benefit of the students here, I'm not one of them, obviously. What are your backgrounds? How did you get interested and get to the level of and the depth of knowledge that you have? And if you're talking to people who are interested in the uses of these technologies, what do you tell them about what kind of things they ought to be studying?
That's a great question. So my background is fairly non-traditional in that sense. My background is actually in fine art, but I know a lot of computer science because I wanted to learn it, and I also wanted to be able to represent those sorts of things in an immersive context. Now, I have been doing programming and adjacent things for like 15 years now, so you can pick it up regardless of your background. I will also say that we have a very compelling internship program where we will take students from any department. We don't expect you to have any advanced knowledge of data capture or modeling or software development, but we will teach you all of those things. And that is a paid internship position. So you can, this isn't really as intimidating as it might seem to pick up and just have in your toolbox. You can do this stuff with your phone. Yeah, and James.
Yeah, and so my background is in geosciences. I've got a bachelor's and a master's in geosciences. I finished up a second master's degree here at the University of Wyoming in GIST and technologies. But I would say even like as an undergrad as a master's student, I remember doing a summer internship with the U.S. Geological Survey. And one piece of wisdom that those researchers told me is to do something else. Everybody's got a degree these days, right? And it's a competitive world for jobs, right? So find something else that you can do to stand out. Get a certificate in GIS, get a certificate in statistics, get some internships under your belt, right? Experience can speak way louder than just an education, right? So there's all these other things that you can do in addition to your current degree to try to one-up that next person, right? So that your application is at the top of the pile, not at the bottom of the pile when it comes to find a job. So.
And just to elaborate a little bit on that, being often on the other side of the table from the hiring process perspective, I am much more interested in seeing work that you have done independently and built as like personal interest and portfolio pieces than that class project that I've seen 100 students from the same department show me. So just like throwing that out there.
So you all mentioned that you're doing your work here on campus, but you also work with clients around the state. What does that look like? How does somebody get engaged with you to, in let's say a particular company or industry? How does that work for you two or your group?
So there are a few different answers to that question. Sometimes we'll work through a sponsored project agreement. That's kind of been the traditional route, but now that we've set up the service center, it should be much easier for us to just have a direct discussion and issue a quote that you can audit those rates. So if we had a service that, let's say that a site needed us to go do a photogrammetric scan, it also needed us to do ground truthing with the field spec, and they wanted a photogrammetry capture, we can kind of a la carte piece that together and give you a quote for that. If you want us to handle the data processing, that's a different fee. So you can kind of build that service to your needs. We don't sort of prescribe these packages where we insist on doing an entire pipeline or something like that. James, if you want to say anything.
Yeah, so our door is always open, right? So if you have a problem that you think we can help you out with, like, come talk to us. We love trying to figure out, we're problem solvers, right? So you might be struggling in a different aspect and we might have a piece of technology that can be beneficial, right? So the first step is send us an email, let's set up a meeting, come talk to us. We'd like to hear your needs, your issues, and see if we can develop a solution for you, so.
I'll also add, as a student, if you aren't necessarily interested in the internship program, but you do have some particular question about a technical challenge that you're facing, please do feel free to reach out. I'll make time. We'll figure it out.
Our office recently received a large quantity of money from the Wyoming State Legislature to record rock art on state and private land across the state. I looked online briefly while you guys were talking about hyperspectral imaging and its applications on pigments. Have you or seen any results from rock art imagery? It talks a lot about art and fine art, but
Yes.
What-
Sorry, I didn't mean to cut you off. Did you have?
oh, and are your rates online, or do we just have to call you for that?
They are not yet online. They will be soon. But call me in the meantime. We actually, rock art is a really interesting topic that I'd love to talk to you about. One of the things that hyperspectral has been used for is identifying pigments that are optically invisible. There was a case recently that actually James told me about where they found like a mummified corpse that had a bunch of tattoos all around, and they couldn't actually visually identify where those were placed, but they used, multispectral in that case, but they could identify all of that pigment placement really clearly. So yeah, I think archaeology and humanities are a strong use case for this technology.
And just to chime in, yeah, there's so many different applications that this technology can be used for. And, we do our best to try to be a little versed in all these different applications, right? But we really come strong from the energy sector. So we can do captures and things like that, but we'd also it might be good to get somebody from archaeology on board or somebody that is a specialist in pigments that can assist us with the analysis, so.
What kind of data do you need to make those Gaussian splatters? Is it just your collected by you, or can you use existing pictures or data to do so?
Yeah, great question. So what you need are a series of photographs that overlap. The more overlap you have, the better. But I cut this talk down a little bit from my usual longer one. One real advantage of Gaussian splatting is that you actually don't need that much coverage. You can get a lot of the interpolated positions from a pretty sparse photo set. It's actually kind of crazy. So if you had historical photos of an environment that have overlap, and ideally the same focal depth, you could probably derive at least a workable 3D facsimile. You don't need a special camera. You don't need any. Yeah, your smartphone is perfectly fine. Also, video is perfectly fine. Like if you took a continuous video of a thing, as long as you weren't changing your focal depth very much, we can just extract frames and make a model from just like a walk around video.
How long on average does it take to develop or render one of these projects?
Are you talking about photogrammetry and splatting stuff?
Either.
It really depends on this. So the capture depends on the scale of the thing. Generating that model more depends on your hardware. So like if you have a modern GPU, like something from the 30 series or better, you can probably generate like overnight at the longest, right? But that's pretty pessimistic.